Welcome to Hot Chips 28. Tutorial 2. 3D Depth for Consumers. From Sensors to Applications.
Hello, everyone. I hope everyone enjoyed their lunch. I had a chance to try that. It was very, very tasty. I'm really excited now to share with you 5 very interesting presentations on 3D depth sensing. 3D sensing has been with us for many, many years, but for the most part, it's been limited to either highly specialized or very expensive applications. For example, on Apollo 15, they had a LiDAR-based system that was used for tracking the command module's altitude as it circled the moon. As you can imagine, it was a very expensive system, very specialized. And when I was studying this slide that I found, I really thought this little annotation here on that graph was very interesting. Complete loss of data due to photomultiplier voltage anomaly. You can imagine the folks in mission control wondering what in the world was going on when that happened. There is, of course, a lot of activity in robotics. In the 60s over at SRI, they had this project where they created this thing referred to as, oh, we need to switch to my slides. There we go. I'll just keep going. So here we have a picture of what was affectionately referred to as Shaky the robot. You can imagine he was given that name, or it was given that name because of the way it behaved as it moved through as it moved. But this was a project over at SRI in the 60s. In today's dollars, it was several millions of dollars. And it had a camera and some rangefinders, and it basically could use computer vision to find its way around, localize where it was in the lab, and find its way around the building. You know, fast forward now to a lot closer in 2011, the folks at Willow Garage created this robot where for a mere $400,000, you can have your own personal robot that you can program and perform tasks for you around the house. And of course, robots are of great fascination in the industrial space. The folks at Oxford here have been working on a robot that can drive around a large warehouse, create a reconstruction of the contents of the warehouse, and use that image to find its way around. Again, a very highly specialized and fairly expensive application. And of course, everyone's favorite topic around robotics and automation is self-driving cars. Again, 3D sensors are an important part of being able to autonomously navigate. But again, currently today, it's still a rather specialized and expensive type of proposition. But there's another trend going on. In 2010, this guy shipped, the Microsoft Xbox Kinect. Now suddenly, 3D sensing was available for your living room. Eventually, 24 million units of these sold. And this is one of the first mass market applications for 3D sensing. And it really introduced the average consumer to what this type of technology could enable. We then saw the folks at Occipital create the structure sensor, an add-on for your iPad that could now enable your mobile device to perform 3D sensing tasks and applications. And in about a month, Lenovo will be shipping a smartphone using the Tango technology that also includes 3D sensing. And now you will start seeing 3D sensing integrated into your everyday phone. And not just all the hardware proliferation, but of course different applications that take advantage of these, this technology. This is a screen grab from a website called Sketchfab. They position themselves as the YouTube for 3D models and 3D reconstructions, where they have over 750,000 3D reconstructions that people have created with their everyday 3D sensors, upload them for sharing, and other people can also download them and use them in their project, their video game, their construction project, or whatnot. So we're now at a point where the 3D sensors are about to take off, and we're going to see more and more applications in the consumer space. And so what we're going to hear from are 5 companies who are in the middle of these of this transformation. PMD creates time-of-flight sensors. So we'll hear from what a sensor company's perspective is on this, this new revolution. Then we'll hear from Movidius and Inuitive, 2 companies that create processors, SoC processors that specialize in vision processing. And then we'll hear from someone from Tango and another person from DotProduct to learn about applications for 3D sensing for both consumers as well as for small professionals. So let me first, I'll introduce our first speaker here. Our first speaker is Bernd Buxbaum from PMD. Bernd is the founding CEO and CTO of PMD, which started in 2002 and is today the world's leading 3D time-of-flight chip technology provider. He has degrees from Technical University of Darmstadt and the University of Siegen, where he's also currently a lecturer. Bernd, why don't you come on up?
Okay, thanks, Larry, for that kind introduction. Yeah, welcome to my talk. My talk is entitled VR and AR Anytime and Everywhere, and what can a company like PMD contribute to these new ecosystems that are coming up. Well, I want to start off with an image that was taken approximately 2 months ago. And what you see here is the President of the United States with the Chancellor of Germany in the background at a booth. And that was an event in Germany. It was the Hanover Fair, which is the biggest industrial and automation fair in the world. It is held every year. And as America was the partner country this year, the President was there. He opened up the fair, and he visited us at our booth. So we were lucky to have him test our technology. And what you see here is President Barack Obama testing a virtual reality class based on a cardboard device. And what we additionally did is we just integrated a small USB PMD camera on top of that device. So the president was able to see his hands in the virtual space. He was able to interact with virtual content by the 3D information that our camera detects. So what is interesting is you just need a piece of cardboard, a standard smartphone, and a 3D camera from PMD, and you can have an application running on that host processor. So obviously, there's not a lot of calculation power needed to do this. In the past, when we had 3D cameras based on stereo or structured light, for example, the calculation often was a problem. So I'm representing PMD. We are a company founded 2002. We are working in the fields of automation, robotics. This is where we started. Now we are moving into new markets like consumer and also automotive. We are a fabless IC company, and we are a chip provider at the end of the day, but we also deliver prototype systems to customers and to prospects. Major shareholder is a company called IFM, also located in Germany, and they are using our technology since more than 10 years in the automation space for 3D cameras or simple rangefinders or stuff like that. So we're shipping every day already since 10 years, and now the consumer market is growing for our technology also. What are we doing? Well, we have a 3D technology based on the time-of-flight principle. So what we do is so-called indirect time-of-flight. We do not measure with a stopwatch the time it takes for a pulse to travel to an object and come back to the camera. What we do is a continuous wave modulation of a light source. For For example, like this one, it could be a laser or an LED. It doesn't matter. We don't rely on the coherence of the light. And what we do is we just switch it on and off very fast, maybe with 60, 80, 100 megahertz, for example. And then we illuminate the scene, and what comes back from the scene is the reflection of the modulated signal that we transmit. And as the light has a certain speed of light, which is very fast, but it's still limited, the distance is represented by a phase shift that is inside that reflected signal. And what we do on our PMD chip, which is shown here, is inside every single pixel, we do a correlation measurement. So we correlate the incoming light with a reference signal that is also used to modulate the light source. And this correlation is done in hardware. It is done directly in the pixel, on the pixel level, and you don't have to do calculations afterwards. You have to do some, but they are very lean. So what we do, obviously, is a convolution of the reflected light with a reference signal. And this is, as I said, realized by the very specific pixel structure that we have that also gave the company its name. It's a photonic mixing device. And as we know, the signals that we use to modulate the light and to also modulate every single pixel, the result within every single pixel is the correlation function. So if we use rectangular signals, as in that case, you can also use other signals, of course. The rectangular signals lead to a correlation function having this triangle form, so you know exactly what you're searching for. And what we did is, we are not really doing a very small shift of the signals between each other, so we take just samples. Typically, we take 4 samples to reconstruct the correlation function within every single pixel. Why 4? Well, the correlation function has 3 unknowns. It is the offset of the function, is the amplitude of the function here, and of course it's the phi, the value that we want to measure, that really represents the distance. So you have 3 unknown variables, so you need at least 3 measures to detect these 3 unknown. If you take 4 samples, calculations gets easier, so typically we take 4. So what we do is, we take 4 samples, so we make 4 measurements, one after the next, and then we fit the autocorrelation function into these sample points. As we know how the autocorrelation functions look like, as we know the modulation signal that we use, we can easily fit this into that sample points. And if there is a time of flight, so a distance that the light needed to travel to the object and come back, the correlation function shifts a little bit. And this shift, this measure phi here, then directly represents the distance within every single pixel. So our pixels are able to really see depth automatically, and we can do this for a number of pixels, for example, 100,000 pixels in parallel on one small imager. What you get is, we always say our imager sees depth. That is true somehow, but if you then want to calculate the real distance value, you have to do some calculations as well. So what we do on chip in the pixel is the sampling of the correlation function, and what we then do on the host system, for example, on the application processor of the smartphone that we use, we do, as I said, the fitting of the correlation function into these sample points, and that results in very easy formulas. And I show the formulas here, so if you want to detect the phase that is representing the distance, you just have to do this calculation, arcus tangens of the 4 sample points in that depicted form, or you can also calculate the amplitude of that correlation function, which is a very interesting information. I mean, if you know the amplitude of the light that comes back from the scene, you know directly how good the measurement is that you're doing. So let me give you an example. If you measure in 1 pixel, for example, a distance of like 4 meters, you also know what the standard deviation of that measurement is, as you know the amplitude of the light that comes back. So that is very valuable information for realizing applications. You know always how good you're measuring. And you always know also if you can't measure in a certain point because, for example, there is no reflectivity in that certain point. So that is very interesting and very valuable information for us. You also get information about the intensity from the background light, for example, sunlight or other light sources that is directly delivered by the chip itself. So it's very easy to calculate depth on a host system using our technology. So there's not a lot of horsepower needed to really do that calculation. And that is one of the reasons why you now can use PMD sensors in smartphones, because also the calculation power that you need to detect the depth information compared to, for example, stereo cameras is really, really low. So what are the advantages and the side effects that you have? I mean, what we do is a sequential sampling of the autocorrelation function, as already said. What is good about that is we don't need a baseline, as you have it with stereo cameras, for example. You just have one camera, one receiving lens. You need an active illumination, that's all. You can build this very small together. You can make very small and tiny modules. They are still very robust and easy to calibrate. So that's a really huge advantage of our technology. You don't need high computational power, which is good. I mean, applications also need computational power, so the application processor has enough horsepower to use it for the applications. And we do the calculation on a frequency or phase level. We do not really make a stopwatch measurement of a pulse that we transmit, which is not easy to do because you need to realize high bandwidths in your receiving chain in the electronics, which also makes some effects and problems. The side effects are, as we are doing measurements one after the next, at least 4 times, it might occur that we have motion blur effects, because if something moves during the measurements or during taking the samples, there could be, of course, a false information. However, you can at least detect motion artifacts and also get rid of these pixel informations if you detect it then. The other thing is we use active light, active modulated light. So what is interesting about that is, as I explained already earlier, the distance information is descrambled from the background light. What I mean is, if we, for example, go out and have full sunlight and we do a measurement with our system, the pixel is on a pixel level able to distinguish between the active modulated light and light that is, for example, coming from the sun. Because it's not modulated with the same signal that we use typically, we can really distinguish these 2 signals. That makes it very easy to even have the cameras work in full sunlight. For example, we ship a product since several years. It's a mobile camera that we, for example, use for harvesting machines, so completely other market. And we see 50 meters in front of the harvesting machine in full sunlight if there is an obstacle and if you do have to react. So another information is the grayscale. So the infrared grayscale image, that is very stable. It's also not dependent from other light sources like the sun. So you have the same grayscale image always independent from the other light conditions that can also be used for many applications. And that makes it very interesting. What are the side effects? I mean, it's an active system, so for far-range sensing, we need more light. It's as easy as that. So if there is no reflection from the scene, and in higher distances, obviously, less light comes back to the camera. The measurement gets worse, so you need to spend more active power to also do a measurement in higher distances. However, I don't want to go too much in detail about that slide, but the system can be adapted in many ways. So if you, for example, say, I want to measure in a higher distance with a camera, you can change several things. You can change, for example, the optical aperture of the receiving lens, which has direct influence. So if you, for example, want to double the range for the same performance for an existing system, you can just use a faster lens. If you do the F number by half, you can then measure the double range with the same performance as before. You can also change modulation frequency on the fly. Our sensor is so programmable and so fast that you really can change on the fly frequencies that you use. You can also change integration times that you use to detect the sample points. And you can, of course, change the amount of light that you transmit. So if you say, I have a camera that is integrated in a mobile phone, obviously it will be a tiny module, so you have maybe only one VCSEL or LED that you use. If you have a camera that will be used, for example, for surveillance, you can obviously spend more LEDs, for example, as you have a bigger housing and stuff like that, so you can also measure in higher distances. So there are a lot of variants that you can do. So our technology is used in many different use cases based on that scalability. What is also scalable is the chip itself. I mean, it's a standard CMOS technology that we use. And for example, we are shipping a product since more than 10 years in different generations, which is a simple laser rangefinder. It's just a piece of silicon. The only thing you need to add is an illumination source. The driver, the processor, the computation, the pixel itself, everything's integrated on that small guy. And it's a very easy one-pixel laser rangefinding solution based on our technology. What you also can have is a imager, for example, with 100,000 pixels. So that's a product we're already shipping since more than a year. It's a CIF resolution, 352 by 288 pixels, so around 100,000 pixels. And that is used already in 3D cameras for robotics. So we sell this product since more than 1.5 years already. And right here in the middle, you see the latest chip that we're launching right now that will be used in upcoming smartphones, for example, in the Lenovo Fab 2 Pro, which will be the first Tango-enabled smartphone on the market later next month. So very scalable in the sense of pixel, number of pixels, pixel size. I said the system itself is very scalable. Also on the fly, you can change by software very much of the parameters that influence your measurement, precisement. So it's a very adaptable technology, and that's the reason why we use this technology in many different markets. Just to give you an example, I show two of our sample cameras here. One is the so-called minicam. It's a camera that we build up to demonstrate that we can use our technology outside in sunlight. It has a measurement range or working range of 15 meters. It uses the full resolution of the 100K imager. It is running with up to 35 frames per second. So it's a camera that, for example, customers use for realizing surveillance cameras. So they take this as a reference design and develop their own product out of it. On the bottom here, you see a more consumer-specific camera. It's a camera PicoFlex. I also have one of the PicoFlex cameras here with me, attached to a standard smartphone, and I will show this later on to you. So that is the camera that we typically use to give it to customers that are working on consumer applications, for example, like Tango. This camera, this guy here, is approximately the same module that will be used by Lenovo in the Fab 2 Pro. The only difference is half of the camera is the USB interface approximately. So this is shipped as a USB camera just to give our customers easy access, plug and play access to the technology and see if it is reasonable or if it is okay for their application. The rest, what you see here in that picture, is standard technology. There's nothing specific. The lens is not a very specific lens. The chip, as said, is a standard CMOS technology. We use different fabs. We use different process nodes. The smallest process node we are in right now is 180 nanometers. We can also go down. There was not a reason to go down so far, but maybe that will change in the future when the pixel resolutions go up. And then we have the USB bridge, a little bit of a housing, and this is what we ship in numbers of like a few thousand a year to customers, universities that want to start play, at least with our technology. So again, it is very robust, scalable, tailored, and that's the reason why it is so good, why it can be used so good in very different applications. So what do you have to do to scale the technology down for a consumer use case? Well, what we did is, of course, we integrated much of the functionality that is needed onto the chip itself. So it's not only the pixel array, it's also that we increased sensitivity by implementing micro lenses on every single pixel. We have digital interfaces to program the registers of the chip and to read out the data directly in the host processor. There is a controller on board that is doing the whole measurement controlling. We have the modulation drivers directly on board, also for the illumination sources that we use, and of course AD conversions already integrated on the chip itself. Another very important point is, of course, the optical path. So the lens that you use, in general, has to be a very fast lens. Of course, as we transmit light, we want to catch every single photon that we transmit. So the lens has to be as fast as possible. On the other side, if you want to realize a product that is usable for example, smartphones, it also has to be very thin, very flat. So there's a trade-off, and you have to optimize this. We did this, and we have, for example, for the Tango application, a lens now that has a barrel height of around 4 millimeters, delivering the Tango functionality. So that is something that is obviously small enough to be integrated into smartphones as well. What you see here is the latest generations of our reference designs. This is the PicoFlex that I showcase later on. So that is the most sophisticated reference design for consumer so far. It has 224 by 172 pixels, field of view horizontally of 60 degrees, and the objective height is around 4 millimeters. The modules that we integrate into smartphones are below 5 millimeters in height, so that is something that is reasonable and that is okay to do. Another thing is the illumination itself. It's very important to have devices that you can modulate fast, that then already have or still have a very good contrast. And also it's very interesting or very important that the light that you transmit is very homogeneous, so that you don't have sharp edges. For example, what you see here is the profile, the light profile of an LED and a VCSEL. So that was the reason why we decided to use VCSELs for the consumer applications. You can modulate them faster. You have a more homogeneous light distribution, and that makes the whole measurement over the whole matrix, over the whole sensor, more uniform and more precise at the end of the day. So what you see here also is a direct effect of changing the frequency. If you use, for example, a camera with 30 megahertz, in that case an LED, or 80 megahertz, in that case a VCSEL laser diode, the frequency is a direct, it has direct influence on the measurement performance. The higher you modulate the light signal and the pixel, the more precise you're measuring. So that will be, for the future, one of the main tasks to realize having higher frequencies, higher bandwidths on the pixel level and also on the illumination level, and that will deliver then even more and better performance in the future. Right now, the cameras that we are shipping, what you see here is, for example, the module that is used in the Lenovo smartphone, or mainly also the same module that is used in the camera PicoFlex. Right now, for the Tango use case, for example, we measure up to like 5 meters with an accuracy of 1%. At a frame rate of 5 frames per second. So that's not a limitation of the technology, it's just a Tango use case. You can also go up to higher frames per second, like 45, 50 frames per second. If you spend more light, as already explained, you can also do better measurements in higher distances. But the Tango use case was really to shrink it down as small as possible and to fulfill these specifications. What I now try is to give you a live demo of that Camera PicoFlex. It's just that USB camera that I was mentioning, and I plugged it onto that standard smartphone here. And it's a Samsung S7 smartphone, and we will see if that comes up now. Let me see. Okay, yeah, it's working. It's working.
And while he's getting this started, if you have any questions, we'll have time for 2 or 3 questions. So go ahead and make your way to the mics.
So just a second. Needs to connect. Okay, so what you see now is the display of my smartphone here. And as said, the PicoFlex is attached to the smartphone via the USB. And I just want to show you what comes out of the camera, more or less the raw data that comes out of the camera. So what you see here is a color-coded depth image. I can change the scale. Let me see. Okay. So what we have here is color-coded depth. So you see the first 5, 6 rows, and the color is representing the depth value. It's a little bit delayed. It's running faster on my display, but what you see here is a little bit delayed. So it doesn't matter. And what I can do, for example, if I take one of the first rows, you see I can just pick one pixel. In that case, pixel number 96, XY111. and it says it's 2 meters 80 centimeters distance with a standard deviation below 1 centimeter. And the reason why I can say what the standard deviation is because I can detect the amplitude that comes back from the object. And that was the advantage that I already mentioned earlier. So I do not only have the depth information, I also have an information about the quality of the measurement. Of course, I can do this in real 3D. So let me see if that is running. So I can have a bird view on the first rows here. You can see it from the side. And that is the information that the PicoFlex, for example, delivers. We also have APIs and middleware that is running on that guy. So if you are an app developer or something, you can have an easy access directly to the camera. And as said, we are shipping these. So if someone of you has interest, just give me a discussion later on after that talk. So thank you very much. I'm finished. Thank you.
We have a couple of minutes for questions. Does anyone have a question, please? If you have a question, please come up to the mic. Is there anyone? I have one question.
Go ahead.
With the progression of Moore's law and as geometries get smaller and whatnot, where do you see some of the opportunities for the future for your technology? Resolution, performance, how do you think about that?
Well, you know, Moore's law is one, but what really is interesting for us for the future is stacking technologies for CMOS images, which is already in the market right now. So if you have the ability to bring the electronics below the detection level in the future, that will be, for time-of-flight sensors, a huge advantage. Because, as I said, we transmit light, and as we also pay for the light that we transmit in some way, we really need to collect every single photon. So if we have a high fill factor and larger pixels, that really help to have the performance on a very good level. So stacking technologies are interesting. Of course, if you go to smaller nodes and if you can shrink the electronics that is in the pixel, you get the same effect. So the performance will go clearly up in the future.
Okay, that's a good message for all you stack die packaging people out there. It sounds like we have one question over there.
Hi, my name is Aditya from NVIDIA, and I have 3 questions for you. The first question is, how do you really detect the phase of the incoming signal? Because it's a standard camera, right? So how do you extract the phase information? The second question is, are you susceptible to interference from other sources? And the third question is, once you get an image, is the image only to be used by a machine, or can you render the left and the right view so that the human eye can also interpret the photograph?
Okay. Well, the first question, it's not a standard camera. So the PMD pixel is a specific photodiode. And what we do is, to make it very easy, we have integrated a multiplier and an integration stage into every single photodiode. So that gives us the ability to demodulate the incoming light. And if you do this with the same signal that you use to modulate the light, you can distinguish between correlated and non-correlated light. What we do to keep the dynamic range up is we subtract non-correlated light during integration. So the dynamic range is only used by the active illumination. That is very, very important, and that is very unique. The second question was, what again? You're right. It's maybe the same explanation a bit. Because, I mean, sunlight also interferes. It's not modulated. It's DC, typically. But as it is not correlated to the modulation we use, it is subtracted. If you have a second device using, for example, the same frequency, you can detect this because we have periods where we don't do an active measurement in between. And if you see correlated signal in between, you can change your own frequency. So you can detect, while you know if you're transmitting yes or no, you can detect if there's someone transmitting on your frequency, and you can change it. The last question, how can you use the data to really make it or give it an impression that the human eye really can see? Well, we do it with a cardboard, actually. So I have one of the cardboard devices here. It looks a bit different than the one that the president was using. But of course, if you have the 3D data, you can do autostereoscopic displays, and you can see directly what the camera sees. If you like, you can see later on a demo where you see the data that the camera detects directly with your eyes. And that is impressive because you really see how precise and how fine the details are, and it gives you a feeling about the quality of the measurement that we are doing.
Okay, great. Thanks, Bert.
Thanks. Thanks, Larry.
Next, I'd like to bring up David Moloney. David is the Chief Technology Officer and co-founder of Movidius, which he started in 2005. He worked for Infineon in Munich, ST Micro in Milan, Siva DSP, and Frontier Silicon. David left Parthis in 2003 to work towards his PhD at Trinity College, Dublin, and his work was on high-performance computer architectures, which was awarded in 2010. David is inventor or co-inventor of over 20 issued US patents and is the author of numerous conference and journal papers. Please welcome David Moloney.
Hello, everybody. We seem to be not getting on my turn laptop here. Okay. So I'm going to give a talk about the technology that comes after the technology that Bernd has so ably talked about. Essentially, how you can take depth images and series of depth images and start to make sense of the world in terms of interpreting that volume. There are a lot of useful things that you can do that enable functionality. Movidius is a fabless semiconductor company, so we produce a processor. We have a stand outside, and we can certainly, if you're interested in finding out more about the hardware, you can come and talk to us outside. In fact, you can see demos that we'll be showing today also. But the talk here is specifically about volumetric data, and it's primarily work that's been done in my team. So, as Bernd mentioned, the availability of mass market depth sensors with the Kinect really opened huge possibilities in terms of reconstructing volumes. And very good work was done with the Kinect at Microsoft in the UK. And in fact, one of the things we'll talk about is the Kinect fusion algorithm, which essentially fuses lots of depth images, integrates them, and creates a volumetric image. Obviously, Movidius has taken part with Google in Project Tango. And Bernd has talked about active sensing, and active sensing is certainly one way of producing depth images. But passive sensing is also, while computationally intense, as he noted, is very useful in that you can produce full color images, and typically, the technology is readily available. So, from our point of view, we don't produce sensors. We work with a variety of different sensors and work on taking the depth images, either helping to produce those depth images in the case where you've got a stereo pair, or taking images, let's say, from a time of flight or structured light image and fusing those into a volumetric representation. And I guess the important thing here is that volumetric representations, as we'll show, have numerous applications in robotics, in AR, mixed reality, and even in things like as banal as security cameras. So, I mean, one of the things you'll notice about most of the space in this auditorium, like in this forest, is most of it is empty. So if you do a LiDAR scan and you start to look at all the voxels in that volume, in fact, most of them are going to contain zero information. So we'll come back to this later on, but if you can take advantage of, in terms of the representation of that empty space, you have potentially massively reduced by orders of magnitude the amount of data necessary to fully represent the volume. And obviously, less data means less computation and means less memory bandwidth and less power. So one of the things that we're going to talk about on the following slides is Kinect Fusion. So I mean, we didn't invent this. We took the software. It's been developed, a platform independent version of the Connect Fusion algorithm was developed as part of a UK EPSRC project called Pamela. And they chose this application as a really good application for driving the development of multi-core processor architectures. So essentially, they've done a really nice job of packaging this up. It's portable in C, C++, CUDA, and OpenCL. So you can very quickly look across a range of different platforms, and you can evaluate how they're going to do. And essentially, you take depth images, you do smoothing on them, you then integrate them, you track the integrated values, and in the center of that loop, you create the kind of volumetric model that is shown on the right-hand side there. So you create this volumetric model of what you're seeing recreated from the depth map. So I mean, we won't go into any more detail than that, but this is the process that's used at the back end of the kind of sensor that Bernd just talked about. So essentially, you have looking here, in SlamBench, you have basically, it runs across all these different platforms. There's C, C++, OpenCL, and so on. And basically, we did some work here to compare from an energy per frame standpoint. Our own implementation was just simple C++, nothing fancy in terms of doing any optimization. Literally get the stuff to compile and work, and we have a demo outside. But the interesting thing is that from a platform point of view, if you're looking at energy per frame, even with that platform, you can get pretty decent energy per frame numbers. We're working to ourselves. I mean, we literally have the demo working in the past week or so, but we're working to up those frame rates by writing some custom code. But it just shows you can take one of these codes that's really been written for, I suppose, academic comparison purposes, and you can get it to work in relatively short order on a mobile platform. So the demo that we'll show, and hopefully I can show you the video here, basically is the one that we're showing outside. And essentially, here what we're doing is taking the output from this time-of-flight sensor. We're basically connecting that via USB to a Myriad 2 board, and we're basically integrating that. And that's basically 256 voxel on a side volume. This is a small scale scene with relatively simple geometry objects, given that the resolution is pretty low. Otherwise, it would start to look pretty blocky. But it just shows you can build something that very short time ago would have required a pretty beefy desktop. You can actually run it in real time on a mobile platform. And our goal is to get this kind of algorithm up running on a few of the vector processors in the design, working at 25 frames per second in the coming month or two. But really, that volumetric representation then is something that you can start to do very useful things with, and we'll talk about that in the coming slides. Also, the same kind of data structures and so on that you can use, you can then apply those to any arbitrary size geometry once you find a way of sorry for the delay here in doing this. Once you find a way of compressing the volumetric information. So essentially, the interesting thing here is if you look at SlamBench, you've got a 512 element on the side. Voxel cube is being used to represent a 5-meter cube with 1 centimeter resolution. And if you basically multiply that out by 4 bytes per voxel, you get to 512 megabytes, which in a very low-cost embedded system is going to pretty much occupy all the memory that you have. So in order to get this, get the data storage requirement down, the route that we went down was to go and develop octree-based storage. And essentially, with an octree, what you do is you recursively divide the structure down into smaller and smaller subcubes until you've reached either you have no geometry in that portion of the image. So you can imagine here, in these portions of the image you have no volume. So you can stop at the very highest level of abstraction. Otherwise, in the highly detailed parts of the image, you can go right down to the bottom of the octree. So you have essentially a tree-based structure that represents the volume. And in fact, what we've done is to use 1 bit per voxel. So we have a 64-bit base element that describes a 4 element on a side cube. We can then store, that's a kind of a natural fit for the processor architecture that we have, in that our Shave processor is kind of uses 64-bit memory and bus infrastructure, so it's kind of a natural unit. But what we can do then is augment that 1 bit per voxel representation with additional information that codes for a group of voxels that contains RGB and the transparency and the truncated sign distance function, let's say, that's being used for integration purposes in terms of producing the volumetric reconstruction. You have other ways of representing the volume as well. Let's say this, if you want to access one of the voxels at the very lowest level in the tree, you actually have 4 levels of indirections. You have to basically read a pointer here, read a pointer here, read a pointer here and here in order to access the very lowest level voxels. But if you want to do things like fast collision detection and so on that you might want to do in some applications like robotics, you can do that at a higher level of abstraction, because clearly you don't need to be able to do that at centimeter or millimeter level. It needs to be at a size that's meaningful for the robot. So let's say half the width of the robot or something like that. Another possibility that you have is you could actually represent the top portion of the pyramid structure in terms of a dense volume. You lose a little bit in terms of memory occupation, but I mean 6 element or 64 element on a side volume is pretty small and easy to store in on-chip RAM, and obviously you don't have to do so many memory accesses, so everything speeds up. So this is the kind of basic element that we're using for volumetric storage. The interesting thing is that once everything is in ones and zeros and you've reconstructed it from your volumetric, let's say your volumetric reconstruction using your dense SLAM algorithm, then you can start to do very interesting things. For instance, if you can do, just by ORing voxels, you can create projections in X, Y, and Z. So we'll get to this later on, but you can do really, really interesting things. You can do convolutional neural network inference based on the volumetric representation. For things like AR and MR, you can create audio models on the fly, which can be, allow you to be very immersive with that kind of solution. You can create maps from the projections that I mentioned, but equally you can refine those maps. So let's say if you have a vehicle, if you have a path, you can basically project the voxels to create these tracks. Then you can basically eliminate the second track because it's wide enough to accommodate the vehicle. And then you basically just need the beginning of each of these piecewise linear segments. So if you want to have lots and lots of vehicles, for instance, collaboratively building high-resolution maps, you can do that with based on this kind of technology. So I'll show you another video now. It's based on this half-square kilometer industrial site north of Dublin. We recreated a structure for motion model and a point cloud based on this, and using drone footage, and essentially we were able to reduce the memory requirement by basically 2 orders of magnitude.
This point cloud is a reconstruction of a plant cement factory located north of Dublin. The point cloud was generated by a drone using structure for motion. The point cloud can be converted into a polygon mesh. This is the standard data format used in computer graphics. However, for just storing volumetric information, this data format is inefficient. This model requires 10 megabytes of storage. The Vola model on the right only requires 120 kilobytes of storage. This is 99% smaller than the polygon mesh. This is achieved using 1 bit per voxel in a sparse voxel octree data structure. Additionally, This data structure accelerates level of detail. This means a coarse version of the model can be used to speed up navigation when a high detail model is not required. This point cloud is a reconstruction of the Platten cement factory located north of Dublin. The point cloud was generated by a drone using structure from motion. The point cloud can be converted into a polygon.
Okay, sorry about that. Go back to our slides again here. So basically, rather than 10 megabytes of data there, we were able to take this footage from a drone and reduce it down to 128 kilobytes, which is clearly at the level where that can be radioed from drone to drone, for instance, or when your drone takes off, you can download that volumetric representation and you can use it as ground truth for your computer vision system, because otherwise, a lot of these computer vision systems, they're still in development. And if you want to have a truly autonomous flying vehicle, you better have some kind of safety net that allows you to second guess what's happening with your computer vision system. So one of the other things that we did based on this volumetric representation was actually to do CNN-based inference. So we built a network. We took the MNIST dataset, which some of you may be familiar with. So it's basically handwritten digits. Jan LeCun developed a network called ANET for the US Postal Service in 1989 while he was still at Bell Labs to recognize these digits. So this is stuff that's been around for a long time. So we took those digits, made 3D models of them, programmatically using Blender, using Python scripts, generated huge amounts of data with X, Y, and Z rotations. And basically this was done as a proof of concept to see, well, can you use this volumetric data 1 bit per voxel? And the answer is yes. We're getting pretty good accuracy with a really, really simple network. It's literally 3 convolutional layers, pooling layers, etc. It's not quite at the accuracy that the regular Linnet gets, but it's literally the results of what was done by an intern. So again, we're talking about being able to use this same data structure for multiple applications. And to have it be low memory, low computational footprint, etc. One of the other things that we can do is we can generate JIT audio models. So this is a pyramid in Yucatan called Chichen Itza, and basically, if you stand 20 meters in front of that pyramid and you clap your hands, you get what you get back is a beam-formed bird chirp. Basically, the Mayans were extremely good acoustical engineers, and this isn't the only example. But essentially, you can take the steps of the pyramid, the propagation time through air, the reflection coefficient of stone. It's limestone in the case of Yucatan because the whole of the land in Yucatan is basically made from limestone, and you can basically build a big FIR filter that corresponds to that. And you can obviously take multiple slices, and you can basically create very accurate models rather than having some kind of lumped model that you might have in a game. So you can do the experiment for yourselves maybe afterwards. Just stand maybe a meter from the wall, speak, and then go against the wall and speak, and you hear the reverberation is completely different. So we believe this kind of technology, leveraging the volumetric representation, will be really useful in AR and MR for basically taking the real room geometry, and let's say you're doing a first-person shooter, to basically have the audio waveform from the gun or rocket launcher or whatever be beamformed by that real environment that you're in. And again, this is kind of a possibility that's afforded by the data structure that we're able to extract in real time. I mentioned already, that you can simplify, a map, and you can basically create a, piecewise linear map because you've already been able to do the projection. The path is wide enough, and how high it is. So essentially, you just need a byte or two to represent, the coordinates of each of these piecewise linear sections. The other interesting thing that you can do when you have lots and lots of these devices, which, let's face it, we're going to see lots and lots of robots, drones, and other devices with these with this kind of technology in it, then you can start to take, the same way as with a SLAM system, you take multiple measurements to infer geometry from them. You can take those measurements, you can put them into a big matrix, and you can do the usual triangular solve or whatever other numerical method you want to basically produce an accurate map. So rather than having to cruise down 101 scanning with LiDAR, you can actually crowdsource maps. So again, this kind of technology allows you to do that kind of aggregation with very low overhead in terms of the communications required to exchange maps. And by the way, you can still take very high quality national or regional level LiDAR scans, which there are in many countries, and you can take those and integrate them, or even, in fact, one of the best pieces of European technology that I've seen is the Sentinel satellites that basically map the whole of the globe down to about a millimeter using interferometry and produce a highly accurate map. So you can imagine being able to voxelize the whole of the planet using this kind of format. Once you've got a low enough memory occupancy for that, and you can start to do inference and a whole bunch of other things, either within the device itself or at cloud level. So essentially, what we're doing here within our product is to basically build support for various different things like the projections that we mentioned for insertion and deletion of points, because there's some overhead in terms of storing and retrieving points in a multi-layered octree. And this is an example, for instance, of the logic that you need to insert a voxel, which is a one bit in a 64-bit volume. And essentially, it's a few multiplexers and implicit shifts for those. And essentially, you take the new updated digit that has, it's a kind of a one-hot representation here, 64 bits wide. You OR that with the old bitmap for memory, and then you can update that in memory. So you can very quickly insert, rather than having multiple instructions to do all these shifts and so on. You can do all that in a single cycle. So I hope this has given you a flavor for what you can do, with depth sensors, taking that data, turning it into volumetric representations, and starting to enable lots of interesting applications on top of that volumetric representation. Thank you.
We have a few minutes for questions. Anyone have any questions? Please move on up to the mic. Does anyone have? Okay, we got someone. While people are thinking about or moving up, let me ask you a question. Mm-hmm. You showed a lot of great videos of some of the potential applications. Which ones excite you the most about where?
Well, actually, I think the JIT audio is really interesting, because I think it's something that there's obviously a lot of games technology out there in the VR and AR, or let's say in the VR space primarily, but they haven't. I'm not sure that there has been a lot of work done in terms of JIT audio. You can even think of using this kind of JIT audio in order to basically build a better 3D soundbar. That's one of the things I have active in my team at the moment. You can imagine if you have a 3D soundbar that has, let's say, passive stereo or even active depth sensing in it, you could use that to basically then recognize who's on the couch and beam them better audio change when their head pose changes and so on. So there's even fairly banal things where you could actually endow an existing kind of relatively low-tech product with some value by adding that type of capability. Okay. The other things would be, obviously, one thing I didn't mention there is you can do physics as well. So if you have voxel level geometry and you have an octree, you can obviously do collision detection very cheaply, and that's another thing that we have ongoing at the moment.
Okay. I think we have a question there, Brian.
Yeah. Brian Chin, OnRamp. I'm really interested in the data representation you have in terms of what can be drawn from like computer architecture in terms of locality of reference. Like if I think of a two-dimensional analogy for like matrices, where you can store in row or column major order. Yeah. In a voxel representation,
it's essentially a three-dimensional matrix. Yes, absolutely. And all we've done here, I suppose, is to take that representation to its barest essentials, which is to either indicate occupancy or non-occupancy, on a voxel level, but you can still code for groups of voxels and keep the higher value information there. So you could have, for instance, audio reflectance for audio models, or you could have rigidity for a physics model in this structure. I mean, it doesn't necessarily even need to be 1 bit per voxel or 2 bits per voxel. You could have 3 bits per voxel if you wanted to include hyperspectral data or other data. I think the really interesting thing here is that you'd have a single representation that you can use for many different purposes. One of the big ones would be machine to machine, in fact, because you can have machines that can communicate an idea of a volume, what that volume contains. You can use it for things like ground truth for your computer vision system. But equally, by doing inference, you can also give some semantic meaning to what's in that volume. So in terms of having really intelligent machines that can interact with their environment, I think this kind of technology is key to doing that. And that's really the reason we're presenting it today, is to try and give people an idea, well, what can you do beyond just having a volumetric representation on its own.
Thanks.
Do we have any other questions? Yes, great. Go ahead over here.
I have one question for the self-driving car. LiDAR is one of the key technologies which has the most challenges, if you have snow, rain, and so on. Yeah. Do you think this could be something which is replacing LiDAR to some extent and which would drive down the...
I mean, that's a real challenging question. I mean, we don't play in the automotive space ourselves. I mean, LiDAR obviously has the benefit of very high accuracy, but I think we're not the only people to think that it's very useful to have crowdsourcing for data. The main problem would be having operation at night without having an actively illuminated system. So I think by definition, for safety critical applications, you're always going to be talking about heterogeneous sensors, maybe some lower resolution active sensors, as well as the passive high resolution sensing, so you can leverage really what the image sensor people are doing in terms of Moore's law. So I think the kind of models that you can build here that we've described are independent really of the front end technologies. You can basically take all of that data, aggregate it, and produce very highly accurate maps. Even at terrestrial level, once you've got the data representation right.
Okay, any other questions? Okay, I think we're good. All right, thank you,
David.
David.
Very much.
Next, I'd like to introduce Dor Zepeniuk. Dor is co-founder and VP of R&D at Inuitive Technology. He's a 20-year veteran of the Israeli high-tech industry. Prior to Inuitive, he served as a program management director at PrimeSense, the provider of 3D sensing for the Microsoft Kinect. Prior to PrimeSense, Dor served as business development and R&D management positions at Alvarion, and as a program manager and system design manager at the Intel Cellular Division, where he was responsible for several 3G SoC projects. Please join me in welcoming Dor.
Thanks, Larry. Hello, everybody. Just quick practice. Okay, so I'm representing Inuitive in this symposium, and let me give you a short background about the company. Essentially, we're a fabless semiconductor startup, okay? The company was established 4.5 years ago, and our mission and our focus is to develop 3D imaging and vision processor for the consumer electronic industry mostly, but not necessarily just for this application. We are an Israeli company located in Israel. We're a very extensive ecosystem around virtual reality, augmented reality, and other types of computer visions applications is being developed in the last few years, and we are very happy to collaborate with our partners either in Israel or in Germany, Japan, and other countries as well. The company is still young, but growing quite fast in the last couple of years. We're already 80 R&D professionals, and we are a multidisciplinary company. We are not just a system-on-a-chip developer, since that in the area that we are active, without developing the entire system around this chip, it's really difficult to sell it. So we are also doing optics design, system design, VLSI, of course, algorithms for imaging, vision, firmware, etc. As I mentioned, it's not just a chip that we are developing, it's a complete solution, and I will touch later on the scope of this solution. Our first product, the NU3000, it's a unique product in the market in a sense that it's combined between 3D imaging or depth sensing capabilities or depth sensing engine with computer vision processor, a powerful one. And this combination is very attractive for virtual reality, augmented reality, robots, drones, and other such applications. And therefore, our solution is getting much traction in the market, and we already our customers are using our chip, first generation chip, for different virtual reality, augmented reality, robot, drones, and other devices development. And today, I'm mostly going to discuss the NU4000, which is our next generation product. We view it as an evolutionary processor solution. It's unique in a sense that it's, again, combining between a very powerful depth engine, a powerful computer vision, computer accelerators, and other good stuff that I will touch later on. A few words about our roadmap. The NU3000 is already in production. And our first customers are going to ship product to the market early next year. NU4000 is our next generation device. It's similar concept. I will touch it later, but it's better in any sense of the product. And the future product that we are now kind of speccing, therefore it's mentioned here as a tentative, is the NU4100, which is a kind of a shrinked version of the NU4000, which is focusing on mobile devices. And today, again, the main topic for discussion is the NU4000, which is a unique device in the market. Let's talk a little bit about the challenges. When we came to design our second generation chip, we done that after a few years of dealing with the different challenges in the market, again, focusing on virtual reality and augmented reality. And what we sense in the market is that the trend is to add more and more sensors. You've seen this in the earlier lectures. There are different depth sensing technologies, there are different computer vision technologies, different applications that require different sensors. And we see more and more sensors integrated into the system. A good example is the Microsoft HoloLens, which is using 7 or 8 different image sensors, depending how you count. So this is a challenge by itself. Many sensors, it means high demand or heavy demand for image processing, for computer vision. These sensors are not there just to see the picture. You need to do a lot of processing on these sensors, and this is one of the challenges that we are trying to address. Heavy computing, in most of the systems, at least the one that we see in the market, the memory becomes a bottleneck, and this is another challenge that we are addressing by our product. And we see advanced use cases in the market, such as gaming, navigation, and other such examples that you see earlier, and these advanced use cases required very low latency. Latency becomes a very critical factor in the product design, and this is another challenge that we have in mind when designing the next generation chip. And mobile use cases is our focus, and therefore, very naturally, the power efficiency is very critical. We are in the consumer electronic business, and the cost, of course, is critical, and you can design a very powerful chip, which is a very efficient processor, But if you're not designing it to be a very cost-effective, then nobody is going to use it for consumer electronics. And our new product, the NU4000, is designed to address all of these challenges, and I will explain how we do that. And before we discuss the specific architecture of the NU4000 chip, I would like to talk a little bit about architectural concept or our architectural philosophy, if you like. What we see, and I touched it earlier, that more and more sensors, higher requirements for computer vision, higher requirement for imaging, depth processing is an heavy computational tasks. And what we see, and we get very strong feedback for that in the market, is that such application as virtual reality, augmented reality, robots, drones, they justifies a dedicated processor to encapsulate the different computer vision and imaging requirements. And this is our focus, how to architect just a device that addresses these challenges in the most efficient way. And the concept that we are adopting is, rather than using kind of a common processing technology for different tasks and different processing duties, our approach is to design and adopt the most suitable processing technology or processing block for the different processing tasks, which means integrating several types of processing blocks, several types of processing technologies, each one of them addressing a different use case or different task in the system. And we see that as a spectrum of processing blocks, starting from a very hardwired image processing pipeline and up to a very programmable and scalable and flexible vision processors. And we have in between stages different flexibility or different trade-off between efficiency and flexibility and programmability. And by combining different types of processing blocks with different flexibility and different level of hardening, we can provide the most efficient or the best power performance trade-off. As I mentioned earlier, the memory become a bottleneck in the system, especially the external memory. And in order to release this bottleneck and enable the system to do more, or enable the chip to do more with the same type of memory or the same memory bandwidth, which is unlimited, of course, we are trying to implement as much as possible processing pipelines in the chip, which are not relying on the external memory. And I will touch it later how we do that. And overall, one of the main architectural goals of our design is to reduce the DDR load, which probably many of you understand how critical this resource is. Based on this concept, we can provide the best trade-off between performance, scalability, flexibility, etc. And we call it a best-of-breed architectural approach. Rather than taking a very powerful GPU and expect this GPU to perform both depth processing, computer vision, SLAM algorithm, and so on, we are adopting different processing technology for the different tasks, and this is why we call it a best-of-breed approach. And now let's touch the chip that we are about to sample early next year. It's the NU4000, and talk about its architecture. In our view, it's currently best-in-class 3D imaging and vision processor. And these headlines means a lot. It's not a vision processor. It's not a depth sensor. It's actually a very efficient combination of both with some other very powerful accelerators. And if we see, looking on the main elements of this architecture, we have 8 different major blocks, and I'm going to touch them very quickly now. First block is the image acquisition engine. This is, I'm starting with a more, say, hardwired block and moving on to a more flexible programmable block. This is a kind of an image ISP, image signal processor, but it's not a color type of ISP that you can see in application processor. It's a dedicated ISP which is designed mostly for depth processing. It's handled two cameras simultaneously in parallel, and perform all kinds of pre-processing tasks which are required for depth processing. The depth processing technology that we are using in this chip is depth from stereo. And this is, as mentioned earlier by the PMD representative, depth processing from stereo. It's a very heavy computing task. This is why we are designing a dedicated hardware accelerator for the depth processing. For us at Inuitive, it's already the third generation of depth from stereo accelerator. It's quite a complicated technology. It has all kinds of nasty artifacts that takes time to learn, to study, and to cope with. And since it's already our third generation depth processor, we feel that we providing a very effective and very powerful depth sensing engine. And what is special about this engine is the resolution and throughput and latency. Since it's a hardware accelerator solution, it can provide very high throughput depths, up to 120 megapixel per second, which means full AD at 60 frames per second or 720p at 120 frames per second, and with a very low latency of less than 1 millisecond latency for receiving a complete depth image of 2 megapixels, which is a very rich and very dense depth map. And the reason that we implemented such a powerful processor, which of course takes its silicon part, is because we actually see these requirements coming from the market. If you look on very advanced gaming use cases, there are such requirements for very dense depth map with a very high frame rate and very low latency. And this is what we are implementing by this hardware block. Next block is quite unique. This is a computer vision accelerators. Typically, you will see a vision processor being used in the industry for computer vision algorithms. What we try to do by this block is to design a very efficient image processing pipeline that is dealing with computer vision algorithms. Specifically, we are looking into SLAM algorithms, which are a very fundamental technology for virtual reality and augmented reality. And what we are doing there, we are gathering multiple algorithms of different visual features detection and visual feature description, which are suitable for implementation by hardware pipeline. Algorithms such as ORB, HOG, FAST, DOG, Freak, Lift, and others. And these algorithms are being processed by a hardware pipeline which is programmable. There are many, many parameters for these algorithms, and the user can program them, but it's done by dedicated hardware rather than storing the data on the DDR and then processing it by the computer vision processor. And you can see these 4 different blocks that I'm presenting on the right side of the chip. It's starting from ISP, then a depth engine, then computer vision accelerator, and then the last one is a vision processor, which is completely programmable and flexible based on IP from CEVA. CEVA is a kind of an arm of the DSP. We examine different type of vision processor IPs. We are not a company which is focusing on developing vision processor per se. Therefore, we are integrating an external IP for that. we find the CEVA XM4 most suitable vision processor IP for our applications. And we are integrating this processor into the chip. This is already a second generation of product for us that is using the CEVA vision processor. Our first generation used the CEVA MM3101 vision processing IP. And this vision processor will run at 800 megahertz and going to provide a very powerful vision processing. Next block is not very unique. It's quite common. It's an ARM RISC processor, which is in use for system management, device driver, communication protocol, etc. This is not the uniqueness of our chip to provide a very powerful RISC processor. Therefore, we're using kind of a mid-low level type of RISC processor. Next block is very unique, very advanced, and actually it's kind of a revolutionary solution that we are providing to the market. We see more and more customers and partners of us that are adopting deep learning technology or convolutional neural networks technologies for the products. We see a real interest in the market for very efficient processing capabilities for this technology. Therefore, we are integrating into the NU4000 a dedicated deep learning processor. It's a processing unit which is completely programmable, which coming with a set of tools that transferring from the offline training tool or framework, tools that provide the real-time execution code for this block. And same as you have RISC processor, vision processor, DSP, GPU, this is a neural network processor which will provide outstanding deep learning processing, especially for embedded processor type of devices. Next block is another image processing accelerator, post-processing engine, focused mostly on depth post-processing functions such as registration between depth images and color images, depth post-processing, image cropping, histogram generation, and ROI cropping, etc. It's a kind of low-level basic image processing functions that we're implementing by hardware. And the last function or last block on the chip is, again, not very unique, though we still have a very special flavor of it. And this is the different peripherals and interfaces which you will see in many other systems on a chip. But we are implementing unique capabilities which are required for the use cases that we are addressing, such as navigation system, SLAM algorithms, for virtual reality, augmented reality, which required very accurate timing mechanism. And this is one of the capabilities of this block to synchronize between different events on the chip. So this is, again, a very high-level view of this processor, which is providing very unique capabilities to the market. And this is just one example for one of the applications that we are addressing, which is virtual reality and augmented reality processing units, or head-mounted displays, or head-mounted device, if you like. Here we show how we can connect to 6 different sensors, a projector for the active stereo depth sensing. We have 2 IR sensors, in this case, an example for OmniVision 720p CMOS sensors. These are IR sensors that we are using for the depth processing. 2 additional cameras for the visual tracking. This is 2 tracking cameras for SLAM algorithm tracking, and 2 other tracking cameras for gaze or eye tracking for sensing the eye movement of the user. And this is part of the VR user experience that you can see in the market for the next 2 years or so. And also we can provide the interfaces to the display. Since in some of the devices, the main application processor will not be located on the head-mounted device, Therefore, our chip can serve as the complete front end for both the sensors and display, and can achieve a much lower latency of feedback from the sensor to the display. Okay, this is a very important slide. I see that I have only 3 minutes to cover that, so I'll try to do it quickly. But here, I'm trying to articulate how this concept works, okay? How these different blocks are interacting between them, and why it can provide a very unique capabilities that you don't see in the market these days. This is the chip with the different 8 different blocks that I presented earlier. And oh, really? Okay, so Larry, tell me now that we have more time. Okay. All right, so I'll do it slower then. So this is again the NU4000 chip with the different 8 blocks that I explained earlier. And this is kind of a zoom or focus on 5 different blocks out of the 8, which are participating in a CNN processing or deep learning, convolutional neural network processing, which is typically being used for object recognition. There are many different types of algorithms and applications for CNN deep learning, but in our world, mostly it's going to be used for object recognition. What you can see here is a kind of a pipeline flow with different blocks that are participating in this flow, and I will try to explain how it works. The input images enter into the image acquisition engine. It can be either 2 IR images for the depth sensing, or 4 different images, 2 for depth, 2 for tracking, and or a 5th color camera for using color for the object recognition, for example. So 1, 2, 3, or 5 different images are entered into the image acquisition engines, where we are performing all kinds of pre-processing functions. After these pre-processing functions, there are 2 outputs from the image acquisition engines. One output is going to the depth processing engine. Actually, this block is generating 2 highly synchronized, aligned, rectified, and balanced images, which are injected into the depth processing engine that are using these 2 well-aligned images to correlate between them and generate the depth image between the 2. So overall, the next block, which is the vision accelerator blocks, this is again a hardware accelerator for computer vision block, this block, receive both visual data or typical or standard images, either monochrome or color images are inputted into the vision accelerators, as well as the depth image, a depth image such as presented by the time-of-flight sensors earlier. And the vision accelerators are using both the 2D images and the 3D images to perform a set of pre-processing functions that are typically processed for a convolutional neural network. Such functions are scaling and resizing of the images, generating pyramids of the image in order to run CNN graph later on, performing background reduction functions, and very important, selecting an ROI for the segmentation, for selecting the ROI on which the actual convolutional neural network is going to be processed. The CNN graph is typically not processed on the complete image, it's processed only on cropped ROI of the image. And the main purposes of this pre-processing function is to detect areas of interest in the image in order to not to run the very complicated and heavy computing process of the convolutional neural network on the entire image. And we're using both 2D-based segmentation and depth-based segmentation. Depth images is a very powerful tool for segmentation and ROI detection. So this is done by the hardware accelerator, the vision accelerator on this block. And this is a complete pipeline inside the chip without using any external memory. From the vision accelerators, the data, or actually the cropped ROI, is moved to the deep learning processor. This block, here we are performing the core convolution neural network functions such as CNN graph processing, acceleration of the convolution process, and eventually object detection and recognition. All this flow between these different 4 blocks is being controlled and configured, programmed, and maintained by the vision processor. But what is special about it, that the vision processor is actually don't need to do heavy processing in order to achieve the object recognition. It has all this hardware accelerator that doing the work for it. It's completely offload, and therefore it's free for many other computer vision algorithms that need to be run in parallel, such as gesture recognition, 3D scene reconstruction, and so on. And the fact that we are using hardware accelerators and processing pipeline for the heavy computing blocks leave us much more headroom at the vision processor for the more flexible and more complicated computer vision algorithms, which typically required over time enhancement, adaptation, and improvement that are critical to achieve by a completely programmable processor, and we cannot achieve by the hardware accelerator, which are focused on the more like low-level basic hardware accelerator. This is another flow for a very typical algorithm that is used for virtual reality, robots, drones, SLAM. Earlier lecture touched that as well. And similar concept is used here. And now I just want to summarize the main advantage of our offering. We designed our solution originally for mobile devices, therefore it is a low power design and a small form factor. Due to using depth from stereo algorithm, we can use both passive system and active system, therefore it can operate smoothly or flawlessly, both indoor and outdoor. Again, as a passive system and also as an active system, depth from stereo technology can enable a very easy coexistence of multiple users in the same room, which is very challenging for other systems such as time of flight and structured light. It's a highly scalable and flexible solution. This is the main topics that we touched earlier. Since it's a very programmable vision chip, though contain many hardware accelerators, they are still highly programmable. Therefore, we can very easily adapt it and modify it and tune it for different types of use cases and applications. And we are not just system-on-a-chip developers. We are working very closely with our customers and our partners to develop together with them the complete system around this chip. And this is a very fundamental part of our offering, the complete system around this chip. I think I touched all of these points earlier. And again, just to summarize the key points, we are providing a very efficient trade-off between power, performance, flexibility, and cost. And this is the key advantages of our solution in the market. So, any questions from the audience?
We have plenty of time for questions, apparently. Okay. So please, if you have any questions, if you can make your way up to the mic. Oh, good. We already have a question over here. Yeah.
Very good talk. Nirmal from NVIDIA. Yeah. For the deep learning processor, do you have, like in terms of bandwidth, floating point operations, is there a measure?
Sorry, can you repeat?
Yeah, is there a performance measure on like how many floating point operations per second?
Okay, it's a good point. We are actually not trying to compete, or say it in a simple language, to show off in a number of G-flops or any kinds of measure. We don't think that this is the most critical factor in this type of solution. More critical factors are functions such as the depth, throughput, and latency. And we do that by hardware engine, which is very difficult to compare with the GPU or NVIDIA GPU capabilities, which obviously it's a very powerful GPU, but it's difficult to compare that with an hardware engine. So we are trying to compare our solution in the sense of depth sensing capabilities, the throughput, the latency, and the resolutions of images that we can process at a certain frame rate and at a certain latency. For example, if you look on a very heavy feature tracking algorithm, such as DOG, differential of Gaussian, which is, if implemented by GPU, will consume a lot of the GPU power. We are doing that by hardware accelerator that enable HD resolution, feature tracking, 60 frames per second with less than 1 millisecond latency. And this is really not something that I can compare with number of G-flops of a certain GPU. So sorry for not being able to give you a direct answer to your question.
Okay, question over here.
Michael During, Tectus Corporation. You've done so many things right, I can't ask any of my usual questions. But I will ask one, which is I didn't get really an impression as to where you were currently in the implementation phase. Okay. When is this going to be available? Have you announced that? Or?
Yeah, sure. Okay, back to our roadmap. Okay, so our next generation chip, the NU3000, is already in mass production, qualified, and we're already shipping 10,000s of units to our early customers, which are going to have products in the market early next year. Next product on the roadmap is going to be samples are going to ship to strategic customers and partners in Q1 next year.
Okay, thank you very much. Sorry I missed that.
Okay, any additional questions?
Oh yeah, it looks like we have another one here.
Shai Galon, Cadmium. So you have there as a bottom line, better cost or lower cost, higher performance, lower power. But this extra performance comes at the cost of, you have a lot of duplicated functionality. So the vision processor, the CNN, the accelerators, all at the end of the day, if you look at the hardware level, it's how many max you can do, right? And so how does that align with lower cost and lower power?
Okay. It's aligned with lower cost and lower power based on the architectural concept. The amount of functionalities and capabilities that we provide on this chip, if you want to implement it by standard processing technologies such as GPU, DSP, or RISC processor, will cost a few times more and will take 10 times more power. And the fact that we are using the different types of processing blocks, starting from very hardware, hardware accelerator, and up to a completely flexible vision processor, enable us to provide a very powerful chip, which eventually provide very powerful processing capabilities for lower power and lower cost. And you can view this solution as a kind of application processor for imaging and vision. Like there are mobile application processors that have ISP, they have GPU, they have DSP, they have CPU, etc. We're also implementing a kind of integration of different processing technologies, but all of them are focusing on computer vision and imaging. Therefore, if you would like to develop a very sophisticated drone or robots that need these capabilities, these deep learning capabilities are a very clear requirement in the market. The SLAM implementation is a very clear requirement in the market, as well as depth. So if you look on all these three different functions, these are very clear requirements in the market, which our customers ask us to provide. And we based on this architecture, we can provide a very powerful processor in a very attractive cost and power.
And the other question is, in terms of programmability, what kind of APIs do you provide? Is it OpenCL, OpenVX, or how do you program all of these accelerators? How can somebody actually use them?
Okay, that's a good question. Actually, I didn't touch that because of the short time for the lecture, but this is a complicated processor, and one cannot do much with it without a very rich set of tools, and this is a very fundamental part of our offering, a different set of tools, APIs, and for example, for the deep learning, the tools support OpenVX interfaces, and for the computer vision processor, we are offering together with SIVA, based on a joint collaboration, a very rich OpenCV library, which is highly optimized for the computer vision processor on the chip. So OpenVX and OpenCV are very fundamental libraries that we are supporting.
OpenVX standard doesn't yet have support for CNNs. It's still in discussions. So,
sorry, I didn't hear you well.
The OpenVX standard doesn't yet have support for CNNs. It's been discussed for the next version, but it's not there yet. So
yes, but from our point of view, the capabilities are there. The tool which is generating the code for the CNN processors is already developed under the OpenVX approach, I would say, and therefore we are going to scale it up in the future.
Okay, thank you.
Welcome.
Any other questions? Is there one more? Yes, one more over here.
This is Guohui from Qualcomm. I have a question regarding to deep learning accelerator. So you mentioned the deep learning accelerator is implemented using hardware. Yeah. But we all know that the deep learning field is still evolving very fast every year. Mm-hmm. And your product seems to be hitting the market at least in another 1 or 2 years. So how do you plan to support new emerging algorithms in deep learning field?
Okay, it's a good question. And actually, this is it's a deep learning processor. It's not a deep learning accelerator. And the focus of this design is to accelerate the low-level computing-intensive functions of the CNN. Rather than implementing a complete CNN framework on this processor, we are implementing the most critical and highly computing-consuming parts, which essentially it's many multipliers which can be arranged in a very efficient manner to perform the basic fundamental convolution functions, rather than a rich CNN implementation. So it's more like an accelerator for the low-level basic functions, which are there for any types of networks. Yep.
Okay. I think we have one more question. Go ahead. Yeah. Here on my right. Yeah.
So I'm Vidyasagar from Qualcomm. Besides AR, VR, drones, are there any other markets that you are addressing with this product? Is automotive a target market?
I'm not sure I got the question.
So is automotive or self-driving?
Okay, the number of application and use for such processor are huge, and probably you know that from Qualcomm as well. The one that I mentioned, VR, AR, robotics, and drones are the most common or most, let's say, commercially interesting ones. But we see many other applications coming from security, surveillance, healthcare, gaming, of course, education, and many, many others. And any device that needs to understand the scene in front of it, to sense the environment, either for surveillance, for security, and other type of application, can leverage such technology, definitely.
Thank you. You have a question over here?
Okay, so I'm Shorin Kyo from Huawei. And my question is that you have mentioned about one target of your processor is to accelerate SLAM.
Yeah.
And however, I suppose that one of the bottleneck tasks for SLAM is the bundle adjustment procedure. And so I wonder why you didn't also include accelerators for this procedure.
Okay, SLAM accelerators, oh, you don't see the presentation, sorry. SLAM accelerators, okay, maybe to answer from a different angle, there is always, when you come to design such a system on a chip, there is always debate what kind of functions to accelerate by hardware and what kind of functions to leave for the software implementation. And naturally, our focus is for the hardware acceleration is for the low-level, intensive computing, yet not too flexible functions. And the areas that or the type of algorithms that we felt are most efficient for accelerators are the feature detection and feature description for SLAM. And the higher layers of SLAMs we are leaving for the computer vision processor.
So you mean that you think that the bundle adjustment portion is not mature at this moment? Is it correct?
I'm not saying it's not mandatory. We consider that as algorithms layers which require more flexibility and are more implementation dependent, and therefore we think it's more suitable to implement them by software rather than by hardware.
Oh, okay, thank you.
Okay, any other questions? Okay, thank you, Dor.
Thank you.
Hi, everyone, welcome back. Let's resume our program here. Next up, we have Ivan Dryanovsk. Ivan is a senior software engineer at Google, where he serves as the technical lead for Tango's 3D reconstruction efforts. Prior to that, he obtained a master's in computing science at Imperial College London and a PhD in computer science at the City University of New York. Please welcome Ivan.
Thank you, Larry, for the introduction, and thank you, everybody, for joining us. Today, I'll present the work that Google Tango has been doing for 3D reconstruction with consumer mobile devices. I'll start by introducing the problem and talking briefly about the Tango SDK that we provide. Then I'll go into more details about the 3D reconstruction stack that we work on, and especially the data structures and algorithms that we use. I'll show a couple of videos of applications that we have, and I'll conclude with a discussion of the developer tools that we make available. So in brief, we are interested in creating accurate textured 3D models of indoor spaces. And our primary focus is to do this in real time and on device. As a secondary focus, we also consider doing some tasks as post-processing offline on device or possibly offline in the cloud. There are multiple motivating factors for this work. One of the most obvious ones is immersive VR and AR experiences. and support for either gaming or professional applications. Another thing that we're interested in is building large-scale 3D maps and large-scale floor plans and support for navigation applications. One of the main challenges that we have encountered so far with this work is that depth sensors for consumer devices tend to be optimized first and foremost for power consumption and also for size and cost. So this creates the difficulty that oftentimes we have to deal with depth data which is partial or potentially noisy. Another issue is that since we're focused on device operation, we're dealing with significant CPU and memory constraints on the device. And we also need to allow for a significant envelope to allow for client-side applications to run alongside our stack. So we can't just max out all the CPU and all the GPU while doing the reconstruction, because we have to allow for the games or apps that use the reconstruction to also run on the processor. And finally, we have the problem of platform diversity. So far, we've had 2 different internal prototypes at Tango. We also have 1 developer kit, and we have 1 consumer device coming out this fall. All 4 of these devices have had a different graphics processor and a different depth sensing solution. So we can't over-optimize for one specific type of hardware or one specific types of depth solution. When we talk about the Tango software stack, we divide our technology in 3 specific areas that we present to developers. And the first one is motion tracking. This is the set of algorithms that enables the device to accurately estimate its position as it moves in its surrounding environment. The second capability is area learning. This allows the device to observe and learn visual features in such a way that when the device is introduced in a space that it has visited before, it can relocalize itself. This allows for relocalization of multiple devices inside the same space. And it also allows for much more accurate motion tracking, because we can correct for any incremental drift that has occurred while we estimate the device's trajectory. And the final category is depth perception. This is the broad name for all the capabilities of sensing the geometry around you. The 3D reconstruction stack that we work on uses all 3 of these building blocks as building components. So let's jump into a bit more detail about our reconstruction pipeline. This is what we do in real time on device. We start with the 6 degree of freedom pose that's computed by the motion estimation system, and we take that as input. The pose is calculated by fusing visual information from features in the camera image together with inertial measurements from the device's IMU. And it's worth it to point out here that we don't actually use any depth for our motion estimation. The reason for that is that to do accurate estimation using depth, you typically need high frame rate, at least 30 hertz, to do good positional tracking with depth. And in a lot of applications, we found that it's actually not worth it cranking up the depth camera to such high frame rate when we can get our positional tracking using a different system. So we typically run the depth at only 10 hertz, and we have our color images also coming in at 10 hertz. All of this data gets fed into our volumetric fusion algorithm. We use a hierarchical volumetric data structure that is based on a TSDF voxel grid. I'll explain all of these terms in a couple of slides from now. Once we have updated our reconstruction using the latest depth and color image, we proceed to extract a mesh from the reconstruction. And we pass that mesh along to client-side applications where they can use it for a variety of tasks. The first and most obvious thing that you can do with the mesh is you can render it, so you can show it to the user. And this is very useful while you're scanning to have immediate feedback of what parts of the environment you visited or haven't visited. You can also do occlusion-based rendering, where you don't render the mesh itself, but use the mesh to hide parts of the virtual scene that you're rendering. And this is very useful for AR applications. If you're doing robotics or assisted navigation, you can do path planning on top of the mesh. And finally, you can do physics and collisions using the mesh as well. And this comes into play especially in gaming applications, where you can imagine a game where the user scans part of, let's say, her living room, and then has a virtual character that jumps up from the couch to the table, or what have you. And in this way, the real environment becomes seamlessly integrated into the game. So we do all of this in general. Our algorithms run at around 10 Hertz. All of this assumes a CPU implementation. There's a couple of tasks that we do offline, and typically when we do these tasks offline, we pre-record all the depth data and color data to disk. And then at the end of the session, we take all those images and depth images, and we stream them in batch into our Fusion. Then we do one final pass where we extract the final mesh, and then we feed it into these two offline algorithms. The first one is mesh simplification, where we generate a mesh with a much lower number of vertices, which results in a cleaner and more compact representation. And we also do texture rendering. The first part of texture rendering is to generate an atlas for the mesh, and the second part is to go through all the color images that you recorded, project them onto the mesh geometry, and generate a high-quality UV textured, or a high-quality UV texture that goes along with the mesh. The backbone of the data structure that we use for our volumetric fusion is called a TSDF voxel grid. And this is something that has been around for a while in the graphics community and has most recently been used by the Kinect Fusion work. So I'll give a brief overview of it here. We represent the space using a three-dimensional voxel grid. And each voxel inside that grid contains the signed distance function to the nearest surface. So the value is high if you're far away from the surface. The value is positive if you're in front of the surface, and it's negative if you're behind the surface. We only do updates near the surface itself, so typically in a truncation region of plus or minus 10 centimeters around the surface, and hence the name truncated signed distance function, or TSDF. The grid is updated by fusing incremental depth observations, and we do that using a moving average filter. So a nice property of this TSDF grid is that the zero ISO surface represents where the estimated texture, or sorry, the estimated surface is. In other words, if you traverse all the voxels in the grid and you find the ones where the value changes from positive to negative, if you extract a mesh along that contour, you will get the best estimation of the surface from all the depth data that you've used. And this is done using the marching cubes algorithm. The output of this algorithm is a triangle mesh. So we use a voxel grid. You can think of each voxel as a small cube on the order of 1 or 2 centimeters in size. For each of these voxels, we store 64 bits of information. We have 32 bits for the signed distance function itself, 16 bits for the function, and then another 16 bits for the weight. And we also store color information directly in these 3D voxels. And we have 24 bits for RGB color, and then another 8 bits for the moving average filter. So this gives us 64 bits per voxel. That's a fairly compact memory representation, and yet if you try to allocate enough space to map out this entire auditorium, you would run it on the order of tens of gigabytes, most likely. So this is not feasible for large-scale mapping. To alleviate that problem, we use a hierarchical data structure where we embed the fine-grained TSDF voxel grid inside of larger volumes. And these volumes are only allocated in parts of the scene that we're interested in. The volumes are typically of size, let's say, 0.5 meter by 0.5 meter by 0.5 meter. We index these volumes using a hash table. And we only allocate these volumes in areas that we visited. So this allows us to exploit the sparsity of space and only represent parts of the environment that we're interested in. Another nice feature of this two-tiered data structure is that we can focus on local updates. And what do I mean about with that? When we receive a new depth image, we can take the virtual frustum of the camera and we can intersect it with our volume grid and mark all of the volumes inside that grid that were actually affected by this depth image. And we can focus all of our calculations only in that region, only on those volumes. Similarly, if there are parts of the scene that haven't been allocated yet, but that we're currently observing, we can allocate new volumes for that part of the scene. This has the nice property that only intersected volumes actually need to have computational updates. Not only that, but only intersected volumes need to have their mesh re-extracted and streamed to the client application. So this allows us to focus our computation locally, and we can map really big spaces without incurring an increasing cost to our calculation. So I'll show a couple of videos which illustrate all of that. Oh, there we go. Okay. So let me pause that for a second. So on the left, you see the pose of the device as it's being tracked in its space, and you also see the real-time mesh that's being generated as the user explores new space. And on the right, you see a top-down projection of that. In this view here, you see the raw data in terms of point cloud that's being given to us by the depth camera and how it gets integrated into the scene. So as the user explores more and more space, we augment the resulting mesh. Here's another view of the same experiment where we show the mesh streaming mechanism. I'm going to pause it again. Each of these randomly colored segments is actually representative of one single volume that's allocated in space. The mesh that you see here is not one giant continuous mesh. Each segment is actually a separate mesh segment that's being transmitted on its own to the client. So as you can see, only mesh segments that are inside the currently visible frustum are considered for updates and for remeshing. So once we can build these meshes on device, we can start pulling in other parts of the Tango stack and building immersive applications with them. Here's an example of that. This is a mesh generated with a Tango device. This is what it looks like when we apply the colors. And here is me inside that same space, wearing a Tango device inside a plastic headset. So as I move around, I can locate myself inside the mesh because we've also recorded all the visual features that Tango uses for tracking. So you see as I walk around, it tracks me accurately inside the room. Not only that, but I can render to myself what the mesh looks like. So this is what I'm seeing as I'm walking around. So you can think of this as like a poor man's virtual reality, only the virtual part is actually captured from the real world. Next slide. So as you might have noticed in the previous video, the colors that we have in the mesh at this stage are not great. It's not photorealistic. And this is because in our real-time, In our real-time algorithm, we assign per vertex colors. This is illustrated here. Now, given that our mesh resolution is on the order of 2 centimeters per vertex, that means that our color resolution is also limited to 2 centimeters. And this is obviously not optimal. So this is where texture mapping comes into play. We do a processing step where we simplify the mesh, and then we do projective texture mapping. We take all the RGB images that we've recorded, and we forward project them onto the mesh geometry. Then we do a weighted average of them, and we get a much higher quality texture mesh. This is one of the algorithms that we have to do offline, and the reason for that is texture mapping is a fairly well understood concept in graphics. However, texture mapping of surfaces that are continuously changing is not so well understood. We're doing some work on that ourselves to do real-time texture mapping, but for now, we're constrained to doing this offline. So these were all scenes that were generated on a Tango device. And when I say offline mapping, all of these processes still run on the tablet itself. So at this stage, we're not actually relying on sending any information up to the cloud or to a desktop station. So let's say we can map out small-scale environments like a room or an apartment. We can apply high-quality textures to them. What's the next step? Well, let's map everything. Let's map this building. Let's map entire cities. And it turns out that there's some logistical issues with creating a really large map with a consumer cell phone. Typically, after 10 or 15 minutes of walking around with my cell phone, pointing it at things, I get tired, right? So the limit of a single session on device is on the order of 10 to 20 minutes. And practically, I can scan maybe, I don't know, a apartment or the first floor of a house in a single session. But if you want to scan an entire building, then you need to take multiple trials, record multiple data sets, possibly do this collaboratively with multiple users. So in this experiment here, we recorded 25 individual trajectories. The total duration was over 3 hours. And then we used Tango's area learning capabilities to co-locate them inside the same space. So all of these users traversed from a different starting point, but we co-register these together in the same frame of reference. Once we have that, we can optimize these trajectories together, and we can take the depth data and build one giant 3D mesh. So to give you a size of scale, this is a mesh at a centimeter level that covers an area which is probably approximately 4 times the area of this auditorium. This is what it looks like when we overlay it on a Google Maps floor plan of the building. And this is the desk where I usually sit doing all of this work. So what are the developer tools that Tango provides for all of this functionality? At the very basis, we have the Tango Client API. This is an API that's available in C, in Java, and in Unity, and it gives developers access on Android devices to the 6 degree of freedom pose, to the color images, and to the depth images. These are essentially the inputs to our pipeline, so you can take those inputs and build your own pipeline on top of that. Then we have the Tango 3D Reconstruction API, again, C, Java, and Unity compatible, which lets you build textured meshes. It gives you access to all the volumetric fusion, mesh extraction, and texture mapping. And finally, we have Constructor, which is a first-party Google application built on top of these 2 APIs that lets you build and share 3D models directly as an Android application. And my final slide here jumps a bit more into platform issues. I don't do GPU programming, so this might sound a little bit hand-wavy, but this is my best understanding of the situation currently. All of our algorithms that we do for fusion and for mesh extraction are highly, highly parallelizable. However, our current implementation, we do these things on CPU. We have experimental implementations where we do this work on GPU. However, on several of the platforms that we worked with, it turned out that we don't have a good memory sharing mechanism between the CPU and the GPU for memory. So just the support for that was not there. So then if you want to run your algorithms on GPU, you need to take your depth images, which typically are allocated in CPU memory, and you need to copy them at 10 Hertz into the GPU. Then you do your volumetric algorithms, and then you need to take the mesh and copy it from GPU memory back into CPU memory so you can distribute it to the client. Now, if the client is only doing, the client application is only doing rendering, then that's fine. We can keep the data on GPU and do our rendering on GPU. But the client will typically be a game, and the game is doing collision avoidance or is doing physics. So the game actually needs that implementation, sorry, it needs that mesh on CPU memory. So we can't leave it on the GPU, unfortunately. And it turned out that these two memory copies here introduce such a significant computational bottleneck that it's not worth it to consider porting our algorithms at its current stage to GPU. So some food for thought for if there's anybody in the audience working on depth camera drivers. It would be great if we get our depth images directly as a graphics buffer, the same way we get color images, so we don't incur this computational cost of jumping from CPU to GPU. Similarly, if you're working on a physics engine for Unity or for any other gaming platform, consider doing things in GPU memory so that we can directly give you these volumetric representations in the form of a mesh or in the form of a field. We can do collisions directly on the graphics hardware. We can do these things in parallel, and we can do them a lot more efficiently. So that's the end of my talk. Thank you all for attending, and we can take questions.
Does anyone have any questions? Please make your way to the mic, and as a reminder, state your name and your affiliation. Any questions? I'll start with a question while people are coming up. Can you talk about maybe some of the long-term research questions that this area has to look forward to?
Yeah, so one of the biggest challenges that we face right now with the entire reconstruction pipeline is that the output of the pipeline is a mesh. And that's useful for a lot of things, but a mesh in itself does not convey a lot of semantic information. So we don't have a good understanding of what is a room, what is a hallway, what is an area that is safe for a person to walk, or what is an area that is usable for you to set up a virtual game. And adding semantic information through 3D meshes tends to be a hard problem, and it's something that is currently gaining interest in the research community. So I think this is a huge potential for further research.
Anyone have any questions in the audience? Because I've got one more. Can you talk about trade-offs between running parts of the algorithm on the general purpose processor versus on a dedicated processor like a DSP or a GPU?
So again, in general, everything that we do is very highly parallelizable. So whatever we can put on a GPU or on a DSP would be a big gain for us. The bottleneck that we've been seeing is memory issues. So there seems to be some platform segmentation about, are we doing things in CUDA, or are we doing things in OpenCL, or are we trying to do things in OpenGL? So yeah, a more cohesive, I guess, approach to doing these algorithms on GPU would be great for us.
Yeah, I have a question.
Dor?
Hi. You mentioned that you are not using the depth data for the pose estimation. So my question is, if somebody can provide you a depth which is cheap enough by means of the power, okay, does not consume too much power, and can be provided at the right, let's say, frequency and accuracy, then would you prefer to perform an RGBD SLAM or not?
So yes, you can implement RGBD SLAM if you have 30 Hertz depth. You can probably get away even with lower depth, but you won't be able to handle very sharp motions on the device. I think it's more a trade-off for power. We tend to get very good information from the fisheye images, which are wide angle, and from the IMU data. And that comes at a lower power footprint than running a depth sensor at 30 Hertz. And since the fisheye camera is part of the Tango spec, it provides a very nice way for getting depth, for getting pose information. So at the end, I think it's a trade-off between how much data you get versus how much power you spend to get it. And so far, what we've seen is that the fisheye has a much better ratio for this trade-off.
Yeah, okay, that's clear. Maybe to expand my question, let's put aside the cost and power for a moment. Would you expect better pose estimation using depths or not necessarily?
I would expect better pose estimation in the sense that the depth would help you get out of some corner cases where the fisheye or the IMU can't handle very well. So if you have an area that has very, very poor visual features, but has rich geometric features, then your visual tracking might fail, but your depth-based tracking would still converge. So it would probably increase the overall robustness of the system.
Okay. Thanks.
Okay, we have a question over here.
I have a question. This regards your backend. You're talking about stitching multiple sessions together to create this mesh. The problem with interior mapping in general is the changes a lot over time. How do you decide if there's any overlap with the meshes? Say a couch was here before, but after a week the couch is gone. How do you make sure like the complete stitching will keep the couch or not keep the couch or something like that?
Yeah, so that's a very good question. Thank you. For our visual-based mapping, we've done some research on what kind of scene changes need to happen in order for the place recognition to actually break. And there are certain things which we are fairly vulnerable to, one of them being, for example, lighting changes. So if you create a map in the morning and then try to relocalize against it in the evening, this is something that's very difficult. In terms of moving individual objects, like if a couch is here and then the next day is in a different place, the relocalization will not fail. It's fairly robust to that. But obviously, any 3D reconstruction that you've built will have inaccuracies. We have a research partner actually at Zurich who's looking into tracking dynamic objects in these lifelong meshing scenarios where you try to identify things in the scene which are static versus dynamic and label them as such, so then the user has expectations about what parts of the scene are about to change.
So in your mesh, you actually identify each object as a type, or is the whole mapping a mesh? I guess the way I'm trying to ask is, do you break up your meshes to categorize each object and then make sure that this is more stable than the other one?
Yeah, so we actually do the categorization at the volumetric level before we even extract the mesh. So each voxel receives a label of whether it belongs to a static object or a dynamic object. Okay. Again, this is not something that we work on internally at Google, but it's in collaboration with a university research partner. But we are aware that all of these, all of this pipeline that I've described essentially is focusing static scenes, and the real world is not static. So yes, that's actually another very good research direction for how do we map out a world that is dynamic.
Okay. All right, great. Thanks, Ivan.
Thank you.
Okay, I'd like to bring up our last speaker now, Rafael Spring. Rafael is an entrepreneur and computer vision engineer. He's co-founder and CTO of DotProduct, where he and his team develop technology and products that make 3D reality capture useful and ubiquitous to solve real-world problems. Before starting DotProduct, he worked in the Google visual search team in Santa Monica from 2009 to 2011, after his augmented reality navigation system for Android was acquired by Google in 2008. During his time at Google, he developed real-time computer vision algorithms running on phones and contributed to Google Goggles, Google Glass, and the early Project Tango. Please join me in welcoming Rafael Spring.
Hello, everyone. My name is Rafael Spring. I'm the co-founder and CTO of DotProduct. And today I'm going to talk about mobile 3D capture for professional applications. So let me give you a bit of an overview over what I'm going to talk about. So the first thing is just 3D capture applications in general. The second part of the talk focuses a little bit more on what we as DotProduct contribute to 3D capturing. The third part of the talk is probably one of the most important ones. It talks about sensors and what we are currently missing in sensors and what perhaps some of you folks can contribute to 3D sensors, because lots of it is right now a chip problem, and so I guess a lot of you folks have some experience in that. I'm going to finish with outlook and trends. There is some stuff on the horizon that's very interesting, so I want to focus a little bit on that too. All right. So we heard a lot about use cases for 3D capturing, and the reason why I find it interesting to be on stage today is because I represent a company that is doing a lot different than what we heard today. So what we heard today was a lot about autonomous cars, AR, VR, post-tracking, mixed reality, 3D content creation, Internet of Things. While those things are very interesting indeed, and we are playing in some of those markets and have technology for that, it's still a little bit unproven. So in the sense that it is on the horizon. Everyone knows it's fantastic and it's exciting, but it's still a little iffy in terms of when it's going to be there and are consumers actually going to pay for it. There is a market though that is ready to adopt right now. And that's the professional market. And there's a lot of use cases in that market, and a lot of users in that market who want to pay real money for this technology. And I will talk about more use cases later, just to give you a little bit of an overview. There's AEC, architecture, engineering, construction. It's as-builting. We have designs, and we have the structures as they are built. There's a difference there. You need to detect that difference and make it accessible. There's planning, there's documentation, there is verification, asset management, huge market. There is people who want to use 3D reconstruction in the field to gain intelligence in the field to make more accurate quotes, or to give or provide measurements to a customer, or all sorts of things. There's reverse engineering, forensics, law enforcement using it for crime scene reconstruction, and so on and so on. So lots of professional use cases. Here's some more. Geo-mapping surveying, that's a little bit out of our scope because we're focusing on short-range sensors. Archaeology, heritage, we have some examples later on that as well. QA, QC inspection, also a little bit out of our focus because that typically requires fixed installations and very, very high quality, high accuracy sensors that are typically very expensive, but we'll get to that later. And also movies and entertainment production, that's also a very large customer of 3D reconstruction. Some example applications of what we're doing at DotProduct. So what you see here, what the hand is holding, is the system that we're selling today. It's called the DPI-8. This is basically our unit that we sell today, and I'm going to give a little demo right after these slides here. And you see all sorts of industrial applications. This is very interesting. It's an old submarine, and this is where they launched the torpedoes. And this is because it represents a very common class of environment that our customers ask us to reconstruct. And so it's very tight, very crammed, not a lot of space to move. It's definitely very hard to access for any sort of major reconstruction equipment that you usually have, like laser scanners and all sorts of other equipment that requires computer and setup and whatever. So it's very inaccessible. And but what we have is this little handheld unit, and so we just went in and scanned that, and on the right you see an image of the resulting model. This is a project that we did in Boston with a company called Skanska Engineering, and it's the Longfellow Bridge in Boston. And I can talk later, maybe off the stage, about all the cost savings that our technology enabled for Skanska. Here's some heritage documentation. Let me give you the mission statement, and then we're going to show a little demo. We want to make 3D capture accessible and usable at scale. So we are a company, we are at the 3D capturing technology and application level. So we heard a lot about sensors and chips. We're not doing any of that. We're a software company, so we want to take depth data that's coming from the sensor, and we want to take advantage of all those chips that are out there to do fancy pre-processing, and then take that product and turn it into 3D reconstructed models, intelligent models, and provide a platform for people and for professional customers to build on and to collect 3D data and share it. That is really what we're trying to do here. Before we go further, let me show you a little demo here. I think I have to switch. All right, wonderful. So this is a scene that I just, a couple minutes ago, scanned outside. Not sure you can see everything, but it's basically the corridor with a podium and some other thing, and the stairs here. It's a little dark, so you cannot really see it, but I'm going to give you a live demo in a second. But the interesting thing is I did this in 2 minutes, literally. So that's the output result after 2 minutes of effort. And to prove that, let me just do it live. So I have a little preview here. You see, this is basically a viewfinder. It's what the camera sees. And it'll just help me pick a start point for scanning. I'm a little limited by that cable here, but let me try it. So I started scanning. I see the system is turning parts of the scene into yellow and green. That's giving me an indication of quality. Oh, it lost tracking, but it'll relocalize, so it's pretty snappy typically. Right, so you see the outline of the scene, the borders as the scene is being extended. Right. You see some areas where the sensor cannot capture any depth because it's too bright actually here. But the table's all right. So let's finish that. And so we have a first model here already. We can see it. It's got all the major things. Some of the black stuff you cannot see. So here on the bottom, there is actually geometry, but it's not very visible because it's black on black. The background's black, so it's a bit hard to see. I can do an optimization that cleans up the mesh a little bit and optimizes the data and runs bundle adjustment, and that'll make everything really accurate. But I need to continue with my talk, so I can do that later. But this is basically as simple as it is. So this is what our customers like about it. It's very easy to use. Let me switch back to the slides here. All right. So those are the markets that we focus on today, because as I said, these markets are ready and very willing to pay money for such a product. We have a stack of technologies. I'm not going to go into detail here. The gray ones are stuff that we aren't doing, obviously sensors and computing hardware, and verticals that can build on top of our SDK API. But what we are doing is we are trying to provide a platform. As I said, we have a sensor abstraction layer. We want to take input from all kinds of different sensors, time of flight, structured light, stereo. LiDAR is coming. That's going to be a big topic. So there needs to be some sort of abstraction layer where we don't have to code against each individual sensor, but can have something that they all share. We have the DotProduct core engine that's all C++ and GPU languages, and all built on top of that are front ends. The one you saw is for Android, so that's Java. We have a new thing coming that's cross-platform. That's going to be QML, and then we have some verticals coming on top even of these front ends, where it's just verticals for different use cases that's built on the front end. So this is a very important slide because other people today have focused on basically reconstructing as you go. And I think the talk by Ivan also focused a little bit on the stuff that comes after the capture, such as mesh extraction. What this is showing is that what we're using is a two-stage process, and it's very similar to, or it's basically takes inspiration from the classical structure from motion and multi-view stereo pipeline. So 3D from 2D. We have 3D from the sensor, but there's still a lot of things in the whole framework that are very useful if you want to go to 3D reconstruction, if you place the emphasis on a final, very accurate 3D reconstructed model, as opposed to stuff like collision detection and or audio modeling or things like that. If you don't need these things, then you can optimize a lot of things and move closer to the classical structure for motion pipeline, which is basically what we're doing. And so there is a separation between an online capture part and an offline post-processing part. And the offline post-processing part runs a lot of these global algorithms that involve all the points that you've collected, involve all the colors you've collected, and comes up with a best possible representation of the world. You do have, though, a preview of the scene right after you capture, and that just helps you see what you have captured. That helps you see that you didn't miss any parts, gives you some judgment about the quality and the level of detail as well. And part of that online part is the user guidance. That is very important for a lot of our customers. This is basically the architecture, a very high-level overview of the online part. We grab a frame, we apply some calibration, and this is also in depths. So depth sensors typically have all sorts of biases. So we need to take those out and to arrive at an accurate depth value. And then we predict the pose, and we get relevant parts of the model that we want to align to. Then we align to that model. We use the geometric and photometric constraints. Once we have the alignment, a very accurate pose to the part of the model, we take the depth data and fuse it in and possibly extend the model. In parallel, we're doing tag detection. That's something I can talk after the on stage, because that's also a very important part for our professional customers. And loop detection in general, map simplification, all these things, they happen in a separate thread, so they're not part of the main loop. Some other things we need to do, and that are pretty unique to our core technology is, for example, our compressed file format. So the scene that I just captured has in our format about 2 to 3 megabytes, and you can literally email that. And a lot of customers do that, and they value our product over a lot of others because you can do that. We have failure-aware tracking. We really want to make sure you don't corrupt the map. So if you ever lose tracking, the technology makes sure you relocalize in the correct part of the scene. You have multi-constraint optimization, a lot of other things I won't have time to talk about, but there's definitely more going on than just the raw 3D reconstruction pipeline. So let's talk a little bit about sensors, because that's a very critical part, and it's also the main reason I'm here today and to get the message out. There's lots of sensors, but there's not many that we can actually use because so many of them are right now still proprietary and vertical. And what that means is, I'm going to explain it on a separate slide. The ecosystem is still very immature, and that's unfortunate. And when we started DotProduct, we had hoped that the ecosystem would mature quicker, but it hasn't happened. Not to the degree that we would have liked. It happens now, and we see players like Inuitive and Movidius that contribute to a flattening of that ecosystem in a more healthy state. But a lot of things are still very vertical. Vertical meaning companies doing everything from sensor to middleware to reconstruction, and then applications on top of that, and then trying to sell that to the end user. And that's very immature, and that's not so desirable, because no company can be good at all of those things. So what we want to have is a more horizontal ecosystem where everybody just focuses on a specific part. And we would like to be on the software side of things, and we would like to have partners that are doing the processing side of things and are doing the sensor side of things. So that would be really optimal. Once we get to that sort of maturity in the ecosystem, then a lot of good things will happen. A lot of business will be created. And so the sensors we're currently able to use is basically the structured light and stereo category. There's been some very good developments, for example, from Inuitive, also from Mantis Vision. Intel has done some good work. Obviously, PMD is a very interesting technology as well. And there's LiDAR stuff coming up. It's also getting miniaturized, but it's a little bit in the future still. So all the ones that are grayed out are now the ones that we cannot use because it's so proprietary and it's so special. So that's just not so good for us. So what are the requirements that we have on a sensor? We want it to be accurate. And accuracy doesn't equal precision, so we want it to be accurate in the absolute sense. And when the sensor says something is 3.50 meters away, it needs to be 3.50 meters away and not 3.60 meters or not 3.20 meters. There can be a little noise, but what we don't want to have is the kind of bias that a lot of sensors have. And that's basically just a matter of calibration, but for the consumer market today, actually it turns out that a lot of camera or module manufacturers don't really care about that sort of calibration. We do, because for our market it does matter whether someone gets a reliable and dependable measurement or whether someone doesn't. We need ruggedness, we need the ability to capture outdoors and in daylight, although we don't have it today. We'd really like to have that. Makes a lot of difference for a lot of our customers. It needs to be easy to use, of course. It needs to be good quality at longer ranges being something like beyond 5 meters, maybe 5 to 10 meters. That would be very good if we had a sensor that would cover that kind of range in good quality. And also the ability to cover spaces quickly, essentially meaning having a large field of view. What it doesn't need to be is look polished. I mean, this the device I just showed you is quite heavy and quite big, but for our kind of customers, that's really, really small. And they like it, and they don't care whether it's polished or whether it looks shiny and whether it has the newest aluminum finish or whatever. They just want it to work reliably and do its job, right? So that's all they want. And they're able to pay a considerable amount of money for that, so it doesn't need to be cheap. So what are the problems we're dealing with today? I've got some keywords here. I'm not going to read them all, but considerable amount of issues that we're having with today's 3D sensors. Going back to the architecture, what is the impact of these issues? Some sensors don't have appropriate registration where the depth and the color are off, and we need to compensate for that. A lot of sensors have rolling shutter problems. We need to compensate for that. Motion blur problems. Issues with lighting where the depth isn't adapting quickly enough, so the tracking gets lost. Undersampling is a big issue. They advertise we have VGA resolution, and essentially what you get is this upsampled stuff that's essentially just QQ VGA or something. And lots of other things that impact the model quality. We have one of the most evil things are depth distortions, and unfortunately those tend to be dependent on temperature as well. So these are basically warpings in the depth image where when you image a flat wall, it doesn't come out flat, it comes out slightly bent and with a donut-shaped distortion. It's probably when sensor manufacturers aren't really putting the calibration into the depth estimation. And a lot of other things that lead to not failures, but inaccuracies in the pose estimation. And that leads to drift in the end. So those are some of the failures that come in when we get suboptimal 3D sensors. Also, in the reconstruction, there is buildup of false pixels around a discontinuity. We call it crust. It's something that's happening also in structure from motion, and those things get a bit nasty if you don't control them. So this is just a graphical illustration. Maybe I should grab the laser for a second and show you what I mean here. So this is basically a trajectory. This is my in Bavaria. My parents have a house in a nice little garden, and I did a loop here around the garden, and I arrived at the end here again. And this is where we see misalignments happening. So this is one surface of the grass, and this is another surface of the grass. It's one and the same surface, but this trajectory here, that's, I think, something like 70, 80 meters. And at the end of that trajectory, we had this drift happening that led to the misalignment of these floors here. This was done with an older version. I think now we can do a little better. But essentially, the issue remains. After a while, you get buildup of drift, and it's not trivial to get rid of that drift, and so you want to minimize that to the degree possible. And it's the reason behind that is mostly because of the mentioned distortions in the sensor in the depth image. It's not so much because we stack up error when we align these images. That's it's just a question of mathematics. You have a lot of measurements, and what you derive are 6 numbers for the pose. So that's not really so much an issue. There's a little bit of that, but not quite much of it. What's mostly causing this drift is distortions in the depth image, and those are stacking up quite a bit more than just alignment errors. There's over-smoothing. That's you always have to with camera-based sensors. There's low-res colors that just aren't out of the prime sense that we're using today as a sensor. in our product, we get QVGA colors. That's, you know, really like yesteryears technology. What we would really like is a partner we could team up with that produces a very reliable RGBD sensor at scale, without the problems that plague the current generation. And the thing is, it's all business now, so it's not a technical problem. Technical problems are all solved. We just need to find a way to make it work economically. As I said before, the ecosystem is very vertical right now, and each of those vertical companies have solved these problems, but they need to capitalize on the investment now, and so they're not so quite willing to cooperate with someone else who wants to take it and just cut off one layer of their stack. So what we want is a mature ecosystem. We want a partner that focuses on building a reliable sensor, and that we can team up with to deliver something to the professional and industrial market. And believe it or not, the economics are really good. We are talking about a very high margin market, a market that is able to pay several $1,000s for a system like that, a market that is able to buy tens or hundreds of thousands of these systems if we give them the right quality. I'm over time a little bit, so I'm going to be quick here. What we're going to see, I'm convinced, if I wasn't convinced I wouldn't be doing this, but I'm very, very convinced that 3D sensors are going to get a lot better. I've seen some very cool stuff, and it's not here, but it's coming. And I'm happy to talk about that off stage or in the questions. So those are just some examples on the bottom that are going to come out. The other thing that's very interesting is going to happen is low power compute. So today we're running on an NVIDIA Shield tablet. It's a great little piece of technology. We use probably about 20% of its computing power for all of the stuff that we do today. So we have the compute, it's all there. The problem that needs to be solved in going forward is to how to deliver that compute with a low power consumption. So the problem is that we can run this thing for, 2 to 3 hours. How can I run this thing for a day or two? That's the question. And so we have seen companies like Inuitive and Movidius that are working on those low power compute solutions. What the challenge is going to be essentially is finding that balance between delivering something that's universally useful for a lot of developers in terms of computer vision and optimizing for a particular use case. And so finding that balance is, I guess, going to be a bit tricky for chip companies, but I'm positive that can be resolved. And then the other thing that's definitely going to happen, and that's been mentioned a lot of times today, and I can just only agree with this, we will see a lot of 3D data coming our way. We will see an explosion of 3D sensors. It's just going to be a lot different from today. We're going to see 3D sensors in basically every device that you can imagine where it would make just even marginal sense. And there's going to be a lot of 3D data coming our way. So the next frontier will be who's going to create a software that handles all these data streams and integrates them into something that makes sense, right? Who's going to derive intelligence out of those big data streams? And in the professional domain, that will mean the static, project-based 3D mapping. That's going to go away over time, and what's going to happen is that we will have a 4D, so 3D over time, digital twin, as they call it. So we will see a 3D model that's changing in real time, and you will be able to see it as it's changing. We will see all sorts of inputs from drones, from handheld operators, from 3D laser scanners, from robots contributing to that digital twin all the time and updating that model. So that's going to be the future of 3D mapping, and that's also what we're developing against. So I think that's it. Thank you.
We've got time for a couple of questions. If anyone's got any questions, please make your way to the mic. While we're waiting, I'll ask one question while he's coming up. So you talked a lot about, you shared a bunch of very interesting applications, as built, heritage saving, stuff like that. Which of those do you think is kind of the low-hanging fruit where you can just come in and just really change that space?
Definitely AEC, architecture, engineering, construction. That's a market that's really ready to buy. Once we give them a solution that's reliable, that has a little longer range, maybe a little more daylight capability. I mean, they're buying today, right? It's they're making our company grow and let us succeed. But to make the business explode, we just get a little bit better sensors, and these guys would be all over us. So that's a very low-hanging fruit.
Question here. State your name and affiliation, please.
Yeah, hi, I'm Zishan Zia. I'm from NEC Labs. And I just wondered, so you made this statement about drift that accumulates over a number of frames or over large loops.
Excuse me, can you go a little bit closer to the mic?
Yeah. So you said something about drift that accumulates over longer paths, and you attributed that drift to sensor noise.
Yes.
As opposed to error that accumulates over frames. And I was wondering if you could elaborate over that. Yeah.
So you want me to elaborate on that a little bit more? Or?
Yeah, because so in computer vision literature, from what I've read, no matter how, even the cleanest sensors, you always have drift. It really is error that accumulates over frames.
Oh yeah,
really
you will have drift. No doubt you will have drift. And no matter how good your sensor, you will have some amount of drift because you have some amount of noise. The problem that I was addressing, maybe I didn't do a well enough job on that, was that the drift that we're seeing is not to the noise that you have on top of your measurement. So let us make a model that your measurement is the real thing plus some added Gaussian noise, right? That's the model that typically most of us make. And that model is not accurate for a lot of 3D sensors, because what is actually happening is that your measurement is going to be the real thing plus some really bad biases, and on top of that you have some noise. And what's causing the drift is mostly those biases and not the noise. So the noise are just really, the noise results in a suboptimal alignment, but that alignment error is really, really small. What's accelerating that drift so badly is the biases. So when you have a depth map that's supposed to be flat because you're imaging a wall, but it comes out curved, then you can imagine you're going sideways on the wall. You're stacking up those curved depth maps. It's going to be a round shaped, right? So that leads to a very quick drift of trajectory. And so whatever can help us take out those biases, that will help a lot reduce the drift and increase the overall model quality.
Thank you. Okay, good. Thanks. I think that's it for questions. Thanks, Rafael. Sure. So thanks. I hope the talks this afternoon gave you all some insight into 3D sensing for consumers and professionals. We heard about sensing and processors and applications. So I hope that was good.